Hello everyone, welcome to today's session. Now let's move on and understand the algorithms in depth. So suppose you have an independent variable on the x-axis and dependent variable on the y-axis. So this is the data point on the x-axis. The independent variable is increasing on the x-axis and so does the dependent variable on the y-axis. And what kind of linear regression line you would get? You would get a positive linear regression line as the slope would be positive. Next is, suppose you have an independent variable on the x-axis which is increasing, and on the other hand the dependent variable on the y-axis that is decreasing. So what kind of line you would get in that case? You will get a negative regression line in this case as the slope of the line is negative. And this particular line, that is the line of y equal mx plus c, is a line of linear regression which shows the relationship between independent variable and dependent variable. And this line is only known as line of linear regression. So let's add some data points to our graph. So these are some observation or data points on our graph. Let's plot some more. Now all our data points are plotted. Now our task is to create a regression line or the best fit line. Once our regression line is drawn now, it's the task of production. And suppose this is our estimated value or the predicted value and this is our actual value. So what we have to do? Our main goal is to reduce this error. That is to reduce the distance between the estimated or the predicted value and the actual value. The best fit line would be the one which had the least error or the least difference in estimated value and the actual value. In other words, we have to minimize the error. This was a brief understanding of linear regression algorithm. Soon we'll jump towards mathematical implementation. But for then, let me tell you this. Suppose you draw a graph with speed on the x-axis and distance covered on the y-axis with the time remaining constant. If you plot a graph between the speed traveled by the vehicle and the distance traveled in a fixed unit of time, then you will get a positive relationship. So the equation of the line is y equal mx plus c. Then in this case, y is the distance traveled in a fixed duration of time. X is the speed of the vehicle. M is the positive slope of the line. And c is the y-intercept of the line. Suppose the distance remains constant. You have to plot a graph between the speed of the vehicle and the time taken to travel a fixed distance. Then in that case, you will get a line with a negative relationship. The slope of the line is negative. Here, the equation of line changes to y equal minus mx plus c, where y is the time taken to travel a fixed distance. X is the speed of the vehicle. M is the negative slope of the line. And c is the y-intercept of the line. Now let's get back to our independent and dependent variable. In that term, y is our dependent variable and x, that is our independent variable. Now let's move on and see them at a mathematical implementation of the things. So we have x equal 1, 2, 3, 4, 5. Let's plot them on the x-axis. So 0, 1, 2, 3, 4, 5, 6, a line, and we have y as 3, 4, 2, 4, 5. So let's plot 1, 2, 3, 4, 5 on the y-axis. Now let's plot our coordinates one by one. So x equal 1 and y equal 3. So we have here x equal 1 and y equal 3. So this is the point 1, comma 3. So similarly, we have 1, 3, 2, 4, 3, 2, 4, 4 and 5, 5. So moving on ahead, let's calculate the mean of x and y and plot it on the graph. So the mean of x is 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That is 3. Similarly, mean of y is 3 plus 4 plus 2 plus 4 plus 5. That is 18. So V10 divided by 5. That is nothing but 3.6. So next, what we'll do, we'll plot. I mean that is 3, 3.6 on the graph. So there's a point 3, 3.6. See, our goal is to find or predict the best fit line using the least square method. So in order to find that, we first need to find the equation of line. And let's find the equation of our regression line. Let's suppose this is our regression line y equal mx plus c. Now we have an equation of line. So all we need to do is find the value of m and c, where m equal summation of x minus x bar multiplied by y minus y bar upon the summation of x minus x bar whole square. Don't get confused. Let me resolve this for you. So moving on ahead, as a part of the formula, what we are going to do, we'll calculate x minus x bar. So we have x as 1 minus x bar as 3. So 1 minus 3, that is minus 2. Next, we have x equal 2 minus 3, that is minus 1. Similarly, we have 3 minus 3 equal 0. 4 minus 3 equal 1. 5 minus 3 equal 2. So x minus x bar, it's nothing but the distance of all the points through the line y equal 3. And what does this y minus y bar implies? It implies the distance of all the points from the line x equal 3.6. Fine. So it's calculate the value of y minus y bar. So starting with y equal 3 minus value of y bar, that is 3.6. So it is 3 minus 3.6. How much? Minus 0.6. Next is 4 minus 3.6, that is 0.4. Next, 2 minus 3.6, that is minus 1.6. Next is 4 minus 3.6, that is 0.4 again. 5 minus 3.6, that is 1.4. So now we are done with y minus y bar. Now next, we will calculate x minus x bar whole square. So let's calculate x minus x bar whole square. So it is minus 2 whole square, that is 4, minus 1 whole square, that is 1, 0 squared is 0, 1 square 1, 2 square 4. So now in our table, we have x minus x bar, y minus y bar and x minus x bar whole square. Now what we need? We need the product of x minus x bar multiplied by y minus y bar. So let's see the product of x minus x bar multiplied by y minus y bar, that is minus 2 multiplied minus 0.6, that is 1.2, minus 1 multiplied by 0.4, that is minus 0.4, 0 multiplied by minus 1.6, that is 0, 1 multiplied by 0.4, that is 0.4, and the next 2 multiplied by 1.4, that is 2.8. Now almost all the parts of our formula is done. So now what we need to do? We get the summation of the last two columns. So the summation of x minus x bar whole square is 10 and the summation of x minus x bar multiplied by y minus y bar is 4. So the value of m will be equal to 4 by 10. So let's put this value of m equal 0, 4, and in our line y equal mx plus c. So let's put all the points into the equation and find the value of c. So we have y as 3.6, remember the mean y, m as 0.4, which we calculated just now, x as the mean value of x, that is 3, and we have the equation as 3.6 equals 0.4 multiplied by 3 plus 6, that is 3.6 equal 1.2 plus c. So what is the value of c? That is 3.6 minus 1.2, that is 2.4. So what we have? We have m equals 0.4, c as 2.4, and then finally when we calculate the equation of the regression line, what we get is y equals 0.4 times of x plus 2.4. So this is the regression line. So here is now you are plotting your points, the actual point. Now for given m equals 0.4 and c equal 2.4, let's predict the value of y for x equal 1, 2, 3, 4 and 5. So when x equal 1, the predicted value of y will be 0.4 multiplied by 1 plus 2.4, that is 2.8. Similarly, when x equal 2, predicted value of y will be 0.4 multiplied by 2 plus 2.4, that equals to 3.2. Similarly, x equal 3, y will be 3.6, x equal 4, y will be 4.0, x equal 5 and y will be 4.4. So let's plot them on the graph, and the line passing through all these predicting points and cutting the y-axis at 2.4 as the line of regression. Now your task is to calculate the distance between the actual and the predicted value. And your job is to reduce the distance. Or in other words, you have to reduce the error between the actual and the predicted value. The line with the least error will be the line of linear regression or regression line, and it will also be the best fit line. So this is how things work on the computer. So what it does is perform a n number of iterations for different values of m. For different values of m, it will calculate the equation of line where y equal mx plus c. So as the value of m changes, the line is changing, so iteration will start from 1 and it will perform a number of iterations. So after every iteration, what it will do, it will calculate the predicted value according to the line and compare the distance of actual value to the predicted value, and the value of m for which the distance between the actual and the predicted value is minimum will be selected as the best fit line. Now that we have calculated the best fit line, so it's time to check the goodness of fit or to check how good a model is performing. So in order to do that, we have a method called the R-square method. So what is this R-square? Well, R-square value is a statistical measure of how close the data are to fitted regression line. In general, it is considered that a high R-squared value model is a good model, but you can also have a lower R-squared value for a good model as well, or a higher squared value for a model that does not fit at all. It is also known as the coefficient or determination, or the coefficient of multiple determination. Let's move on and see how a square is calculated. So these are our actual values plotted on the graph. We have calculated the predicted value of y as 2.8, 3.2, 3.6, 4.0, 4.4. Remember, when we calculated the predicted value of y for the equation, y predicted equals 0.4 times of x plus 2.4 for every x equal 1, 2, 3, 4 and 5 from there. we got the predicted values of y. So let's plot it on the graph. So these are the points, and the line passing through these points is nothing but the regression line. Now what you need to do is you have to check and compare the distance of actual mean versus the distance of predicted mean. So basically what you're doing is calculating the distance of actual value to the mean to the distance of predicted value to the mean. So there is nothing but r square, in which mathematically you can represent r square as summation of y predicted value minus y bar whole square divided by summation of y minus y bar whole square, where y is the actual value, yp is the predicted value, and y bar is the mean value of y, that is nothing but 3.6. Remember, this is our formula. So next, what we'll do, we'll calculate y minus y bar. So we have y is 3, y bar as 3.6, and we'll calculate it as 3 minus 3.6, that is minus 0.6. Similarly, for y equal 4 and y bar equal 3.6, we have y minus y bar as 0.4, then 2 minus 3.6, it is 1.6. 4 minus 3.6, again 0.4, and 5 minus 3.6, it is 1.4. So we got the value of y minus y bar. Now what we have to do is take its square. So we have minus 0.6 square as 0.36, 0.4 square as 0.16, minus 1.6 square as 2.56, 0.4 square as 0.16, and 1.4 square as 1.96. Now is a part of the formula that we need. We need yp minus y bar value. So these are yp values, and we have to subtract it from the mean of y. So 2.8 minus 3.6, that is minus 0.8. Similarly, we will get 3.2 minus 3.6, that is 0.4, and 3.6 minus 3.6, that is 0. 4.0 minus 3.6, that is 0.4. Then 4.4 minus 3.6, that is 0.8. So we calculated the value of yp minus y bar. Now it's our turn to calculate the value of yp minus y bar in the whole square. Next, we have minus 0.8 square as 0.64, minus 0.4 square as 0.16, 0 square 0, 0.4 square as again 0.16, and 0.8 square as 0.64. Now as a part of the formula, what it suggests? It suggests me to take the summation of yp minus y bar whole square and summation of y minus y bar whole square. Let's see. So in submitting y minus y bar whole square, what you get is 5.2 and summation of yp minus y bar whole square, you get 1.6. So the value of r square can be calculated as 1.6 upon 5.2. So the result which we'll get is approximately equal to 0.3. Well, this is not a good fit. So it suggests that the data points are far away from the regression line. So this is how your graph will look like when r square is 0.3. When you increase the value of r square to 0.7, so you'll see the actual value would be closer to the regression line. When it reaches 0.9, it comes more close. And when the value of approximately equal to 1, then the actual value lies on the regression line itself. For example, in this case, if you get a very low value of r square, suppose 0.02, so in that case, what we'll see that the actual value are very far away from the regression line, or you can say that there are too many outliers in your data. You cannot focus and think from the data. So this was all about the calculation of our square. Now you might get a question like, are low values of r square always bad? Well, in some fields it is entirely expected that r square value will be low. For example, any field that attempts to predict human behavior, such as psychology, typically has r squared values lower than around 50%, through which you can conclude that humans are simply harder to predict under physical process. Furthermore, if you ask what value is low, but you have statistically significant predictor, then you can still draw important conclusion about how changes in the predictor values are associated with the changes in the response R. Regardless of the R squared, the significant coefficients still represent the mean change in the response for one unit of change in the predictor, while holding the other predicted in the model constant. Obviously, this type of information can be extremely valuable. So this was all about the theoretical concept now. In the next session, we work on the coding part. If you have any doubt, add your doubt in the comment section. Thank you so much for watching.